planets further grow, maybe also by pebble accretion, here the green arrow, they can start accreting gas significantly if the disk, the gas disk, is still there. And then migration, I'll come to that. And here, if the protoplanet cannot make it to the giant planet, it might also end up as something like the Earth, a bit bigger. Here is a short visual story, a bit more visual story of planet formation. So we start somewhere in a dense molecular cloud. So this would be the dark blobs here in the infrared. Nowadays we would have James Webb images of that. I should add this. But now we go to simulations of the formation of stars, and just by angular momentum conservation, it is required that a disk forms around the star. At the beginning, it can be very massive, maybe 10% of the mass. So clumps in the disk parts can become gravitationally unstable, which you saw quickly. And now, over longer timescales, fractions of a million of years, you then evolve the dust in the disk, and now you can see a bit visualized here how a planet can start accreting material, and it would first accrete solids, and only if it becomes massive, it can accrete gas. It has to do that over a time scale of maybe up to 5 million years before the disks are observed to have dissipated, and then only maybe a debris disk like this here remains afterwards. And obviously the planets in the system, which then still evolve over giga years of times. So this was short, quickly about planet formation, and now we think often about planet formation in the context of exoplanets. On the right, you can see here a diagram getting populated over time, which is how we usually show exoplanets with function of mass, period, orbital period, or distance to the star. And you saw large chunks of data released at once. This was the Kepler Space Telescope here, which also populated now the low mass regime, not only giant planets, which are obviously easier to find. And in terms of techniques, there's a large number of planets which was discovered by the transit method, and which is also the data set I will compare to today. And I now show you planet radius versus distance, so very similar diagram, but in this case, planet radius, which is known if the transit method is used, because it blocks a part of the flux, and this depends of the star, which depends on the surface of the area that is covered, so obviously the radius of the planet. So the transit method can measure the radius relative to the stellar radius, and it reveals the data now, the statistics reveal that there's kind of an underdensity here, this blue triangle, which is sometimes called the Neptunian desert, or Neptune desert. It's usually interpreted as, since there's a clear dependence on orbital period, it has to do something with the star, right? The closer you are to the star, the more broad this gap is. So the interpretation is that here there's photoevaporation taking place. I'll come back to that. And up here is usually, it's not a clear case, but likely stellar tides, which influence the planets and make the planets move into the star, which is why there's only few planets kind of in the process of migrating to the star in this regime. Another underdensity is kind of between the giant planets, 10 Earth radii, and maybe between 10 and 5 Earth radii, here marked with yellow. This would be a prediction of planet formation, namely that if you accrete gas, the increase the relative increase increases as you get more massive. So just because the gas contracts under self-gravity, planet gets more dense and can then accrete more gas. Um, Once you reach the critical mass, which is about the same as the core mass, so 10 Earth masses in envelope, 10 Earth masses in core, something like that. This is a prediction for a long time from planet formation theory, but it's not quite clear whether this is statistically significant. Although it looks like there is a gap here, it's in this parameter space. It's also influenced that those giants up here are just very easy to detect also from the ground. So they're clearly overrepresented here. So maybe it's not such a clear case. What is statistically significant, and the only feature we know for the low mass planets, so not the giants, is the radius valley, as we call it, or the Fulton gap, or photoevaporation valley. And this is an underdensity at around 2 Earth radii, and it was known thanks to the Kepler mission 2017. And it separates kind of these planets up here, which we call sub-Neptunes, maybe 3 Earth radii on average, 3 to 4, and the Earth and super-Earths below, which are below the 2 Earth radii. And I mean, you can see there's less planets here, but based on this data here, just on raw from the exoplanet archive, you could not really see, but some publications claim that there's a stellar orbital period dependency here. So we know we have some features in the complete exoplanet demographics, but we can also start to characterize planets. And one interesting paper, which is related to what I showed today, was from Luque and Palais last year, where they showed that there's like two groups of planets around low mass stars, though. So for low mass stars, it's the relative signal. The signals are larger because it's all relative measurements, relative measurement of radius, relative measurement of mass to the relative to the stellar mass and stellar radius. So low mass stars give you the opportunity to really probe into the regime where you have Earth-like planets, Earth mass, Earth radius planets. So if you do that and you only filter out everything with large error bars, you see that there seem to be like two categories. One is one is sub-Neptunes, or really large planets. Then some planets line up on this 50% water line, and then the rocky planets below, with consistent with Earth-like composition. And these planets here, the water worlds, would be really interesting. And it's not quite clear whether this is really water, or it could also, you could get the same radius at the given mass with just less, smaller core and more hydrogen helium instead of water. So it's always degenerate for the individual object, but for a population, for a statistical approach, you might get something out. This really motivated the project I talk about today. So what did I use? I used the planet formation model developed in Bern and Heidelberg, which is for now what I present today is basically modeling the steps from planetesimals, protoplanets to giants or terrestrial planets, and it includes orbital migration. So this is the formation model, and we have to give it initial conditions, obviously, which is the conditions of the protoplanetary disk, and these we take from observations. There are the observations with ALMA and some other measurements of very young objects. We did that in a series of papers in 2021. And I will actually not talk too much about them, but you can read it all up. We can compare to various surveys and constraints. What is done is, as I mentioned, we start with planetesimals and embryos already distributed in the disk, and then we let them grow. And it's always around single stars, no binaries, and we then follow the also the evolution of the planets. So we have an n-body code, but also after the n-body code stopped after about 100 million years, we follow the evolution of the planets over time. But what the model looks like is something like here on this mass semi-major axis diagram. Uh, went really quick at the beginning. You had those 50 embryos in this case growing, and then everything migrates inwards sometime. So all the planets migrate in. You saw the chains here pop up, which is mean motion resonances, and the color code gives you the water fraction. So you see the blue planets here are really large amounts of water in them because they grew in the cold disk and migrated inwards. So the circles here is the TRAPPIST-1 system, quite famous, um, but the constraints actually changed since I plotted this diagram. So this was an individual simulation, but we do that 1,000 times. So we simulate 1,000 systems for these studies. Now, to come back to the radius valley, what is hypothesized as the kind of the standard model to explain this radius valley, so this underdensity of planets at 2 Earth radius, is the following picture. You would have a sub-Neptune with a rocky core and a hydrogen-helium envelope, and you have photoevaporation of the envelope. Photoevaporation is high energy radiation hitting the surface of the gas and accelerating individual particles, heating up individual particles. And in the regime we describe it in, where this is efficient, it's usually driving a hydrodynamic flow out of the Roche, out of the potential well of the planet. So this is the picture, and how this would scale here, as reviewed by Owen, is if you have a rocky planet and add a little bit of atmosphere, it would be removed very quickly. So it's very efficient. The relative loss, it kind of decreases in time, because if you add more envelope mass, this is still only less than 1% in mass, it just takes more time to remove the envelope, but the planet doesn't change much in size yet. Up to the point where it's really the size of the planet gets dominated by the envelope, and this is where the mass loss timescale reverts. So here it's reverting, and then if you add more envelope mass, the planet really significantly gets bigger, and this means it absorbs more flux, and the timescale of removal is then faster again. So the loss is then faster. So this is then here. These planets are really losing efficiently their envelope mass at around 1-to-1 mass fraction. If you increase the envelope mass even further, it's basically the case of a giant planet. The gas is no longer is much denser then, because it contracts under its own weight, and you really have a stable envelope again, just because also the gravitational potential is just much larger. So here I also visualize that the core actually is also contracted. This would be at the constant core mass. So if you think about this picture, how this then gets translated to the population of planets, is that planets at the radii here, 5 to 8 or so, the sub-Neptune desert I spoke about before is called the evaporation desert. Those are those planets here. They have about 1-to-1 envelope to core mass fraction and lose their envelopes efficiently. Then there's a pile up in this regime, which about 1%, at about 1% envelope mass. And if you reduce the envelope mass further, they are stripped completely. And this still makes a significant change in radius, although in mass it's very little removal. And this regime here, kind of below the mass loss time scale of about 100 million years, is then the evaporation valley. Maybe you wonder why 100 million years. This is the time scale over which the star is really active, and the young star is really active and produces a lot of high energy radiation. So it's not the full time scale up to current present day, which is giga years. So this is the picture, and this works quite well. But there's a problem, which is what I showed before, and at least we have a problem with our simulations, because we include orbital migration, and then we get those planets with water. Here, in this picture, there was no water, right? It's hydrogen helium envelopes. But we get water-rich planets, and the reason is orbital migration of planets, which I maybe quickly explain. You have a planet moving through the disk in the protoplanetary disk. Gas is still present, and then the gas outside of your orbit is going this direction, which means the gravitational potential of the planet creates a little overdensity, and this then makes kind of a wake. It's like, the analogy is a bit like a ship going through water. You have really a wake here from the perturbation of the planet, although the gas doesn't need to physically touch the planet, but it's still the same kind of thing. Inside of the planet, the direction of the flow is different relative to the planet. The gas moves faster, so the planet kind of moves downward in this image as seen by the gas inside of the planet. So this gives this kind of shape here of the two spiral wakes. And those are overdensities of material. So they also exert a gravitational pull, although it's not a huge force. It still can be significant if you calculate it. And this wake here, the outer wake, kind of wants to decelerate the planet. The inner wake wants to accelerate the planet, and it turns out that the torque exerted by this outer wake, usually for typical disk conditions, winds, is stronger than the inner one, which means the planet loses angular momentum and goes inwards. So this is then inverse migration of the planet. Under some conditions, also with the horseshoe orbits here, the material on those orbits here, indicated here, there's also outer migration possible. So the fact that we observe exoplanets in systems and they're close to mean motion resonances gives a bit an indication that orbital migration is a thing, because with orbital migration you can really kind of, what I showed in the video, you can have this chain of planets migrating in, and then because the whole process is not very rapid, they really get the chance to be locked in mean motion resonances, which you usually don't have if you just exclude migration. But although theory predicts this for a long time, since the 90s, there's no clear observational proof that orbital migration is really acting in the exoplanets. But in our models, it does, and what it does was also indicated a bit before, is that we have planets growing in the outer disk, migrating inwards and form water worlds. Why is that? If you look here at the sublimation temperature of water, plotted against well, here the thick line is the temperature in the disk. You see at about 2 AU in this kind of disk, outside of 2 AU, you have water as ice, and then a planet which accretes rocky material can also accrete the water in this whole region, which is most of the disk, right? Where most of the planets grow, and this map here, the red color shows outer migration, blue color shows inward migration. The planet would do something like that. It would grow here, maybe also here, and then it goes along the white border of this region. It can also go a bit further out. And then at about 10 Earth masses, migration really becomes efficient. You see here the timescale drops below a mega year, and this means the planet no longer grows, but instead migrates inwards. And this is kind of almost a factory of 10 Earth mass water worlds, which happens in many, it's not just our model, if you set up the model similarly, use the same prescriptions for orbital migration, you always get this kind of prediction that there's water worlds. So does this kind of planet with a rocky core and water ice, how does it fit in the picture? Is it the possible sub-Neptune candidate? Which is kind of what Luque and Pale suggested, right? That this is another population, at least also present. So we wanted to test this. We used our formation models, the population synthesis that we already published in 21, and we recalculated the evolution of the planets with updated atmospheric escape, and the ice was treated as the water was treated as condensed ice, following the equation of state, polytropic equation of state of Sarah-Seeker. So something very simple. And then we applied the observational bias that the Kepler space mission has. It cannot detect all the planets, large enough and also not too distant ones to get the. And we applied this bias in all the details. And what we got out was this kind of radius versus orbital period diagram, which is completely wrong. Well, so this is without bias. So this is just pure directly out of the simulations, but already that is clearly showing that we have a lot of planets here. The blue planets are the ones with water, those water worlds. And they're at 2 Earth radii. And they really have a peak at 2 Earth radii, where we should have a valley. So we did not only not reproduce, we even counter-produced the radius valley. We completely off. If you want to shift, if you want to fit a valley, it would be somewhere between 3 and 4 Earth radii, between the water worlds and the hydrogen-helium planets. Well, in principle, it depends on the mass distribution. If you would make them more massive here, those planets here, you could maybe, but then you would also have not only a radius valley, but a mass valley, which is so far not observed. So we think it's not possible. This was also the conclusion of other works before, Mortacini, for example, and sometimes also by Owen. So this picture is inconsistent, and it could lead to the bigger conclusion that no planet migration is not happening, and planets have to form inside the ice line, right? Or at least not large-scale migration is not happening. But in principle, this only excludes water ice. And if you look at the phase diagram of water, and I overplot sub-Neptune, although at the very close to the star, but this is typically where the planets are observed, close to the star at a few days orbital period. The temperature on the surface is maybe 1,000 Kelvin, and in the interior it's 10,000 Kelvin. And so the phases with ice, they are down here, they're below this blue line here. Those are the high, so this is normal ice down here, and here are the high pressure ices, right? Although they can occur at a bit larger temperatures, it's still very far from where the temperatures are in our sub-Neptune. So we model the interior of the planets in our models. Well, here is the start of the rocky core, and then it will continue as rock. And the ice, or the water, in this case, water vapor, is following this kind of curve. So it's to be precise, it's supercritical water, because the critical point is here in this regime, and then up here it's even super ionic. So it's a supercritical water and not water ice, would be the correct phase for almost all of the planets which have been observed, and especially it's actually for all of the planets from this Kepler dataset around hot sun-like stars, right? Um, so yes, and to make it worse, you would also have the greenhouse effect of the water itself. So you would also enter runaway greenhouse. So it's really true that the whole water is evaporating. So we used the wrong equation of state before, so we want to try again. If water is evaporating, there's reasons to believe that it was also mixed quite well with hydrogen and helium, so we modeled it as completely mixed with hydrogen and helium. So you have this kind of structure, you have a rocky core, and then a mix of supercritical hot steam with hydrogen helium, also hot gas. Um, and the question is now, can our unimodal mass distribution, so no double peak for the masses, reproduce the observed valley with this kind of interior structure? So we had to tweak a bit the evolution model to take this into account. We also included escape of water, although I have to admit, one would, no good tables exist yet, so it's really just quite large extrapolations that we have to do here, but this is the best we could do. Yeah, we used this new equation of state by Haldeman et al. To really model the interior phases, at least, correctly. And what we got was really much, much better. I mean, we expected it to be better and to recover a radius valley, but it was really quite a precise match to the observed valley, which was we couldn't have expected that completely. So we were pleasantly surprised that it matches really well. We have a 2 Earth radii. We get the valley, and it has a little slope, not maybe not as strong as some that are reported in the literature. And we have then the valley then separates the rocky planets, pure iron and silicates, and from the water-rich planets. And the blue points are actually those which don't have hydrogen helium at all, and the orange ones down here, they still have this mix of water and hydrogen helium. So most of the orange points here, at least in this radius regime, are also containing a lot of water in this simulation. Now we can apply the bias of Kepler and see how well we actually do quantitatively with this model. And so the data looks like that. This is synthetic. This is observed. You get kind of the right overall features, although the Kepler data has an overdensity here at 10 to 20 days, and overdensity in the synthetic data is a bit too close to the stars. So planets seemed to have migrated a bit too far in our simulations, which is something interesting to correct. So it's not a fit to the data, right? So we didn't expect to match it perfectly, but it's still in terms of radii, we really get a good reproduction of the observed and synthetic radii. And here as a histogram kind of shows that. And maybe also noteworthy is that the radii drop, the, uh, the planet occurrence drops after 3 Earth radii, similarly to the observed one. And this was something which was not always reproduced with just hydrogen, helium, and rock. And there were publications favoring some magma-ocean interactions here to explain this. But in our simulations, this is just a natural thing that happens. Basically, because water is denser, you don't get a large spread in radii for those water-rich planets. We can also do a statistical test, Kolmogorov-Smirnov comparison, which would then say within 30 days you cannot say that they are not drawn from the same distribution, although in principle the observed and synthetic ones are drawn from different distributions. It's almost almost a match. But outside of 30 days, there's a few differences. So that's what it is. Now, one can think maybe the only important thing is that some planets have water and supercritical water envelopes, and the others are rocky. So the sub-Neptunes have water, super Earths are rocky, but the evaporation, photoevaporation, still played a role. So this photoevaporation of planets in removing kind of unphysical envelopes in our models, because if you grow a planet in a gas disk, every planet in principle can have a gaseous envelope, so hydrogen, helium, and water in this case, um, and even very light planets, planets with very low mass planets, and so without photoevaporation, we get this kind of too large scatter of planets, and we really need to populate the rocky planet peak with those planets out here, to move them down to the rocky peak, and also to remove those unphysical here. So you see a few, which is just one Earth radius, and so they at 10 days orbital period, so very hot, um, they would lose their envelope mass. So this is kind of going back to the picture of Owen, to remove those, pile them up here, remove those here, pile them up here. So this is still acting and still shaping the radius distribution. It's just not the only effect anymore. So the compositional effect is also there. So with that, I can conclude the part about this radius valley. We used updated planetary population synthesis models, and we think the scenario hydrogen, helium, and rock only is possible, but also the scenario with mixed steam and photoevaporation, and the sub-Neptunes would then contain water, is also possible, is what we say in this work, which is accepted but not published. I'm sorry about that, but hopefully it comes out soon. And what we could exclude is that the water is in condensed form for the Kepler comparison. So in this data set where Kepler did the observations, and no escape is also no photo evaporation is also not possible. And in the future, what is now coming is, of course, the James Webb Space Telescope. It will do these kind of observations which are visualized here, or it's already done, it has already done that, also for some Neptunes, which is very interesting to see whether it finds water. And although it probes a layer quite high up in the atmosphere, so a lot of modeling is still required, but there seem to be some indications that what they call high metallicity envelopes are required to fit the data. So high metallicity envelope is likely a lot of water in the envelope, and the implications are, of course, also that orbital migration, if this is really established, it's just a few first results, obviously, but the implications would be that uh, orbital migration is happening in many systems, and this would then also mean that at some point, a bit at colder temperatures, you would have those planets with oceans and large oceans, and maybe life on ocean planets. So with that, I think I take questions, unless you want me to go on.
Thank you very much, Remo. Very interesting talk. So we have some time for questions. You can unmute your microphone and ask your question if you want. Well, I'm not an expert on this field, but I was wondering, for example, what is the role of giant impact in the evolution of super Earth and sub-Neptunian
Yes,
planets?
yeah. It's a very good question. It was kind of also suggested as an alternative to photo evaporation to strip planets. So you can remove via giant impact the atmosphere of the planets. That's important. And in our simulation, I didn't say it. It's included, and this is the reason why we sometimes have pure water here instead of always water and hydrogen helium mixed. So the blue points here, they lost their hydrogen helium because of an impact, and this is maybe also a shortcoming of the model that we want to improve on in the future, is that the formation stage we took from this population synthesis from Emerson, Hoover, and so on. And in the formation stage, the giant impact would happen. And what was included there was, however, always that water has to remain on the planet and hydrogen helium can escape. So they lost their hydrogen helium, but they might have also lost some of the water. But we didn't include that yet. So that's why they're blue points here. And you can kind of see that this is a really relevant effect. It happens a lot. Um, and it should be treated more consistently by our modeling. Um,
Thank you.
I think that's how I thought about the giant impact. And for formations, it's obviously also important to grow the terrestrial planets.
And what kind of stars do you include in the simulation? Just like M-type stars or other kinds of stars?
So this was for the comparison to Kepler, and Kepler was really sensitive to FGK stars. So we used solar mass for all of them. So it was a solar type star for all of what I've shown, but obviously I did an investigation on the stellar mass dependency of the overall population, 21. So I'm very interested in M stars as well, also because you get this nice data that Luke and Pale presented, the higher precision there from observations. So I did a little bit of investigation. But this is a bit preliminary. Try to reproduce also the data from Luke and Pale, a bit updated here. So in terms of mass and radius, whether this picture that we have now with mixed steam and hydrogen helium also fits with this data set. But I have to be a bit careful here. I just assumed it's always supercritical vapor as well. But actually, around M stars, this is not such a clear case anymore. For most of the planets which are observed are still hot, but I mean, maybe you saw it in the news. There was this potentially habitable planet in the habitable zone. So obviously, this is where it's then already colder. And for M stars, we find planets which are also at colder temperatures. But then I identified some regions which don't yet seem to match. So I don't have a clear conclusion whether this is something in our formation model or the evolution model. Broadly reproduced planets, I get synthetic planets where the observed ones are, but the model predicts planets further. Those are maybe a bit further out. They're maybe not a concern because this is not a homogeneous survey. This is just observations from all over the place. So maybe they will come once they find planets at longer orbital periods. But these planets here in zone B and C, the kind of more massive ones, they are a bit concerning. And maybe this means orbital migration happens a bit differently or something like that. So this is to be continued. But this would be for M star. So I also had simulations for M stars.
And do you expect to find these kind of planets around binary or multiple systems, or?
Yeah, there's relatively few around observed circumbinary planets. So interesting would of course be the close binaries and then the planets orbiting both stars at the same time. If the binary is very far apart, I expect kind of the same situation. So very far means maybe 1,000 AU and more. Then it's kind of as single stars. So I think our models that we shown apply for those distant binaries, but for close binaries, there must be a regime where planet formation is really perturbed when the binary separation is also about a few AU, right? Then probably it's very hard to form planets at all. Um, at least core accretion rocky planets. And then if the binary is then um, very close, uh, I don't know yet, but there's a project going on. Hopefully, we know a bit better. There must be some effects then. Yeah.
Yes, thank you. And along with ALMA, what kind of other instrument do you use for the analysis?
So so for constructing the initial conditions, ALMA was really helpful to give us an idea also at which time to start, right? So the disks which are best observed with ALMA are already probably the systems where planet formation already happened. So I kind of try to include this as an output to our models. So it's not an input anymore, but the disk is also an output. And then we start, right now we start with initial disk masses which were found for +1 objects with the VLA actually, because the VLA is a bit longer wavelength, and then the disk is not there's less extinction probably, so you get an actual estimate. So it's not optically thick anymore. That's what I want to say. So for ALMA, it's actually the very young stars are then soon optically thick, so you cannot get a good estimate on the total mass in the system. But with the VLA, it's a bit better possible, although it's at lower resolution. And yeah, for the planets themselves, the discovery missions are always interesting. Now this is really dominated by TESS data here, or test candidates that were then followed up from the ground, like Harmonious. And so for M stars, this is really also a nice set of data for us. Uh, I think you can get more constraints even from this mass radius, even though it's much less planets. It seems to be a bigger challenge for us even than the Kepler data. Kepler was obviously from the Kepler space mission, led to the discovery of this nice radius valley feature. And now James Webb is our hope to verify whether these compositions are right. Although, yeah, it's not trivial to get the bulk water mass fraction which we predict. But my feeling is like we predict really not just a percent or so. We really predict. You see the color bar here. Half of the planet is water at formation, and this should be somehow you should get it out with maybe a combination of mass radius and atmospheric spectroscopy. It should be possible to test this.
Great. So if there are no more questions, I think we can stop here. Thank you very much for joining us, Remo.
Thank you for having me.
I enjoyed it a lot. And thank you very much for everybody for joining us. So see you next week. And thanks again.
Bye
Bye bye, Remo. Bye. Thanks.
Bye, thanks.